I'm Marty Key with RJG, and today we are going to take a predictive process sheet, which was done through simulation using our machine parameters and our material data sheet, which we have right here. And we're going to enter the values that were pulled from simulation in order to be able to predict the process. We're going to enter that into our machine here and see how close that we get to what we actually need for a good quality part. So the first place that we're going to start off at, and we've done a few things up front, is we're going to look at our mold temperatures. So off of our material data sheet, we see that our mold temperature requirements are roughly 49 to 65 degrees Celsius, which translates to 120 to 150 degrees Fahrenheit. Right now I've got my thermolator set at 130 degrees Fahrenheit, so we're good there. So the thermolator, or temperature control unit, what it basically does is circulates water at 130 degrees through the mold. Now, depending on the type of material that you use, that temperature will fluctuate. Different types of material will require different mold temperatures. Plastic injection molding is a transformation process. So here in our barrel, we're taking plastic, and in this case, our barrel is about 450 degrees. We're melting solid pellets, turning them into a liquid form, injecting them into the mold. So 130 may not sound like it's all that cold, but in relative terms, when you're talking about 450 degree plastic, we are cooling the plastic from 450 degrees down to 130 before we may eject the parts. Some other things that we'll get off our material data sheet. So in the predictive portion, we have to set our plastic temperature. So right now our barrel temperatures, it says that off the material data sheet, it wants our melt temperature to be around 218 to 260 degrees Celsius, 425 to 500 degrees Fahrenheit. So if I look right here, off of our predictive sheet, we're at 450 degrees Fahrenheit, and I've got my barrel temperature set for that exact number. Okay. So now I'm going to go through and start entering some information here in order to be able to put in the information we need to see how close our predictive sheet is here to making a good quality part. So the first thing that I'm going to do is enter the shot size, which is 1.695. So that's how much plastic we'll put into the mold. Then our decompression. Decompression is just how much suck back, or we're kind of preventing drool and sitting our check ring off of that suck back. We'll also enter our transfer at 0.395. So transfer is where we go from speed control to pressure control. My melt temperature I've already set. We talked about that earlier on the 450 degrees. Screw recovery time, it says around 15 seconds with my back pressure at 700 PPSI, which is plastic pressure, or the pressure in front of the screw. Now this is an electric machine. We don't have an intensification ratio, so any pressures that we place inside of the machine here are going to be actual plastic pressures, or what may be known as specific pressure. Screw delay we've got in here is a second. Our screw speed should be about 3.3. .3 inches per second. Going down through here, our cooling time should be about 16 seconds. Our clamp force is right at 17 tons. I've already got that set. We've already gone through the clamp up process. So we pretty much have all our information for the most part off of our predictive setup sheet entered right here. So the first thing that I'm going to do is just kind of purge the press out and talk about some of the movements. So again, as we purge the press out right here, I'm going to run it, and we can just kind of get an idea of we're building a shot right now, so what we're doing is we're rotating the screw and starting to melt the plastic. So inside of this barrel, we have a reciprocating screw, which just means that the screw rotates or turns as it goes back. Once it gets ready to inject, it goes into a lock position and moves forward. So to help melt the plastic, the screw is rotating. As it rotates, frictional heat helps to melt the plastic, along with electric heater bands that cover the blanket or cover the barrel. In front of the screw is what we call a non-return valve. The most common type of non-return valve is what we have here, which is a check ring. So this ring goes into the back position during injection, and it keeps plastic in front of the screw, so we don't have any leakage or blow-by that makes it come back up the barrel. As the screw rotates and turns and we're building a shot, that valve opens up and allows plastic to move in front of the screw tip and build a shot. So this is what's causing our plastic to be melted. Roughly 80% of the melting process is done through frictional heat. The other 20% is done through electrical heating or the heater bands. So I've got my shot built up, and what I want to do in order to be able to start the machine is get a lot of this old plastic that has been sitting in the barrel. It takes, on most machines, anywhere from 20 minutes to a couple of hours in order for that barrel to heat up to get the operating temperatures. So right now, I'm just trying to get all that material that's been setting in there during the heat up process out. So I'm doing what is known as purging the barrel. Okay, so I'm going to do this a couple more times. And as we're doing it, I'm going to take a general melt temp reading. This won't be highly accurate of what we're running because I'm purging it so fast. Right now I'm at 73 degrees at room temperature, and I'm going to just build one more shot. And as that's coming back, we'll kind of get a reading off of what our temps are right now. I'm just working around a little bit. Again, this isn't really how you would want to take an accurate temp. I just want to show you close to what our temperatures are. So right now, even after letting it set a while, I'm pushing about 380, right around 400 degrees. There's about 415, somewhere around in there. So we're getting really close to my operating temperature. So rotate the screw back, we'll build up one final shot, and then we'll start processing the mold based off of these settings. Now, one thing is that I want to check first is we're going to go from our shot size, which is 1.695 inches, to our transfer position. And again, our main control here is speed. So we have that set at 3.3 inches. When we hit this transfer position, what some machines may call V to P or velocity to pressure, we're going to quit using that speed as our control, and we're going to start using pressure. Okay, so right now I have the second stage pressure off because I want to see what my fill-only parts look like. So, got my barrel coming forward now, mold's clamped up, and we're going to shoot these parts and see exactly what we get out the front half, if it's close to what we want to see for a fill-only part. So when we say fill-only, what we're looking at there is if you kind of equate it to driving your car home from work, you never want to really pull in and have the back of the garage wall stop you from going forward. You kind of want to slow down before you pull into the garage, so you've got control. So that's what we're trying to do right here. If you were to pull in really fast, or we were to shoot really fast onto the back of the cavity, we could build up excess pressure inside the cavity, and that would potentially cause a flash inside of the tool because we're building up too much pressure. So I can see a little bit of imbalance here, but I can see that most of these parts we're going to call them kind of full, but we do have really bad sinks across the back. and we've got a little bit of a short shot right in here. So that's, we're fairly close whenever it comes to our fill only portion. We can feel comfortable with what we're doing. I'm gonna let it make one or two more shots just to verify that our fill only's looking pretty good. So this is a really good one here after we've stabilized. You can see that our part is just barely short right here. So that's a really good fill only part. I would call this completely acceptable. So we're roughly 95 to 98% full. I'm gonna kind of weigh these and get a good idea of what our weights are gonna be here. This is something that you'll kind of want to document, and we're gonna compare these to where we're at, what we have predicted. So we are looking for a weight of 12.735. Right here I've got 12.315. So I'm about 0.4 of a gram off. I'm going to let it go at that. First stage can kind of be pretty objective. So no real massive changes that I'm going to make with this. All I'm really going to do now is just throw some pack and hold on here. And the pack and hold are our second stage pressure, so we can finish filling this part out, and we'll see how close we get to the predicted process. So right now everything's fairly close. I'm going to start looking at what they call for on hold pressure, or our second stage pressure, and they are calling for roughly about 5,500 psi. So I'm going to put that in. Our fill time, which was our predicted fill time, was supposed to be 0.441 seconds, and right now we're at 0.48 seconds. So we're 0.04 seconds off from our predicted point. So we're really very close to that. Here's our next shot. I don't think we quite got everything on this one right here, but on the next shot we should see some, so we saw our cushion. So what we're talking about when we say cushion, as we come forward, we have to have some extra material in front of this screw whenever it injects so it can transfer pressure. If we have no extra material, what we call cushion, at the end of this screw, we're not going to be able to transfer any type of pressure. So we see that our cushion dropped. It went from 0.33 to 0.155. On our simulation, it called for a cushion of 0.121. So we're really close right there. Just about 0.03 inches off. So right here is our full part that we got from our by adding pack and hold pressure to the process. Here's another one just to look at it and verify. You can see the parts are completely full now. We also have, we've gotten rid of our sinks. Visually, they look acceptable. So let's just compare it to weight-wise, what our simulation called for. Our simulation called for somewhere right around 15 grams. And again, our fill only parts, we're very close. So we're about 14.91, somewhere around in there. So we're just shy of those weights, but you know, we're talking about 0.09 grams off. So very close as far as what our prediction called for and where we're at right now. So that gives you a brief description of how we would take our simulated or our predicted process that was pulled from simulation. We've entered that process into our molding machine, and we've developed a good starting point, a good general robust process that we would now test limits on through the simulation. So this would save us an a lot of time as far as process development and getting a baseline for our process using the simulation tool. Thank you.